so section 8.1 is a review section on different integration techniques that we've learned throughout chapters 4 and 5. We review these because we're about to need them kind of as a collective to build upon for different integration techniques in this chapter. So yeah, this is really nice that this is just a review section. So, all right, let's just dive right in. So if we want to evaluate this integral, I think most of us by this point think of substitution, right, as our kind of our first integration technique that we're going to go to, and that's exactly what we're going to do. So we're going to let u be this stuff under that radical, and that's because you can kind of already see that that derivative is going to be up here. So let's let u be that 1 plus 3 sine x, so that du is 3 cosine x dx. Very, very nice substitution comes out of that, because we just get du over the square root of u, bringing that u, that square root of u up to the numerator, making it a u to the negative 1/2, and then just using the power rule for integration. Remember, you just add 1 to that exponent and then put it over that number. So that'll be u to the 1/2 divided by 1/2. Remember, divided by 1/2 is the same as multiplying by 2. I substituted back in for u and changed that 1/2 power back to a square root. If you wanted to leave it as a 1/2 power, that's perfectly fine as well. Next up is another substitution, but this one's going to involve some e-business from chapter 5. So if we let u be this exponent up here, this cosine y, my derivative of cosine is negative sine y, so I just have an extra negative to contend with, no big deal. I'm just going to divide both sides by that negative sign. And then that substitution will give me e to the u, and then these two are negative du. I just took this negative constant multiple out here, and we know the integral of e to the u is just e to the u, and this constant multiple of negative 1 is just along for the ride. And then, of course, substituting back in for u, and we end up with that as our final answer. So, all right. Let's start getting a little bit messier here. Tangent squared, that is not an integration formula that we know. If you look at your integration formula sheet, that is not on there. However, we can use a Pythagorean identity to rewrite tangent squared into something that is more easily integrable. So if we replace tangent squared with its Pythagorean identity of secant squared x minus 1, the actual Pythagorean identity is 1 plus tangent squared equals secant squared. This is just an algebraic manipulation of that Pythagorean identity. So replacing that, we get this integral. Now, this one is much nicer because the integral of secant squared, ooh, that's a good one. We know that one, right? We know that one because we know the derivative of tangent is secant squared. So the integral of secant squared is just tangent. And then this 1, if we integrate it separately, just the integral of 1 is just going to be x. And then just a plus c at the end there. So with some of these trig things, if it's something that you cannot integrate, then you have to go back to kind of like the trig identity stuff that we did way back in like pre-calc, and replace this with something that you can integrate, be it with a Pythagorean identity or with some other type of trigonometric identity that you can replace it with into something that is, you know, easily more easy to integrate. Okay, so speaking of a different trig identity, don't go crazy here. Don't try to split these up into two fractions. You cannot do it this way. You cannot split up a denominator like that. If this were in the numerator over some common denominator, absolutely. You can split up a numerator of addition or subtraction as long as each fraction has that same denominator. You cannot split apart a denominator. So instead, what we're going to do is let's rewrite this in terms of sines and cosines, and let's see if we can rewrite this into something that's easier to integrate. So secant we know is 1 over cosine, tangent is sine over cosine. All right, so I get this big complex fraction business over here. These two fractions have the same denominator, so I can combine those into 1 plus sine theta all over cosine theta. This is 1 over a fraction, which is the same as the reciprocal. So it's like 1 divided by this fraction. We know dividing by a fraction is multiplying by its reciprocal. So this big mess right here is more easily written as just that reciprocal. This is the same as this, but much nicer to integrate, because now we can just let u be that 1 plus sine theta, the derivative being cosine theta d theta, and look at how easy that is once we get it into this nicer form. It did not start off pretty, and it fought us along the way, but then once we got it into this nicer form, it was a really nice substitution. So we get this integral of 1 over u du, which we know is the natural log of the absolute value of u plus c, and then just substituting back in for u. So some of these may be just a substitution, some of them may need some trig, be it like a Pythagorean identity or some other type of rewriting of a trigonometric expression. And then we have this one. I really like this example because it's 3 examples in one that really demonstrate how a small change to your integrand can make for a humongous change in how it's integrated. These all kind of look the same, but notice the numerators. This one's just 4, this one's 4x, this one's 4x squared. Changing that by just that numerator by just a little bit is going to make a humongous change in how we integrate each one of these. So we're going to do these one at a time just to see the differences in here. Okay, so this first one with just this constant of 4 up top, this is a really nice straightforward arctangent kind of integral. That 4 is just a constant multiple, so if I take that out, then I get this, nicer arctangent form of 1 over x squared plus a squared. So if a squared is 9, we know that means a is 3. So if you look to your formula sheet, you get this formula over here of 1 over a arctangent u over a. In this case, my u is x. And then I've got that constant multiple of 4. Of course, I could have multiplied those together and did 4/3. I just chose not to. So this one with just that constant up top was an arctangent. As soon as an x comes into play, now this is no longer an arctangent. This is just a straight up substitution. So if we look at part B, this is just a substitution. If I let u be that denominator of x squared plus 9, du is 2x dx. So the way that I handle these, you may do it a little bit different. I chose to divide both sides by 2 and then just kind of leave that 4 in there. You may have chosen to multiply that by 2 and multiply that by 2 to force that to be a 4, and that's correct as well. There's just kind of different approaches to how you do these. So I did that to where I left the 4 in there and then replaced x dx with 1/2 du, and so that became a 2, which is the exact same thing that would have happened if you had approached this a little bit differently than I did. So just wanted to let you know if you do it different, it's not wrong. So we get this 1 over u integral, and we've seen that before. That's just a natural log. So we get that natural log of the absolute value of u, and then substituting back in for u. Now notice that with this, x squared plus 9 is always positive. So I really don't even need those absolute value bars. So if you see some answers and they don't have absolute value bars, it's because this this argument is already always positive for all values of x anyway. You know, take any number and square it and add 9 is always positive. So you don't need those absolute value bars. And then lastly, save the best for last here. That 4x squared over x squared plus 9, whoo! This one is so messy, all right? Because the degrees of these are the same, we're not able to use just a nice substitution. It's not an arctangent because we have this x squared up here instead of just a constant. So we have to use polynomial long division to rewrite this quotient into a different rational expression. Okay? And we're going to need to do this every time the degree of the top is the same or bigger than the degree of the bottom. We're going to need to use that polynomial long division. I shouldn't say every time, a lot of the time. So dividing that bottom into the top, I said x squared times what will give me 4x squared. Well, that's 4. And then distribute. 4 times x squared is 4x squared. 4 times 9 is 36. As with normal long division, you have to subtract in this step. So that's the little circles in there, which is me subtracting. So that these terms zero off. This was a positive when I multiplied, but it changed to a negative when I subtracted that. So I get negative 36. Now, here's what this means. In this long division, all right, so whenever you do long division, if you did something like, say, let's say you did 5 into 17. All right, so it goes 3 times. 3 times 5 is 15. You subtract, you get 2. Do you remember how you wrote this as a mixed number? Because remember, this is 17 divided by 5. As a mixed number, this is the quotient and the remainder over the divisor. And in mixed number form, this 3 and 2/5, what we don't write is that plus sign that's understood to be there. So it's the quotient plus the remainder over the divisor. So 3 and 2/5 is equal to 17 over 5. So much easier with numbers. When I throw, polynomials in there, it becomes a lot messier. But it's the same general idea. This original integrand can be written as the quotient plus the remainder. Now, I just said plus, but there's a minus here. That's because my remainder is a negative number. I just didn't write plus a negative. Remainder over divisor. The divisor is what's out here. If I were to get a common denominator for these two things and then combine into one fraction, I would get this thing back. But instead, I'm splitting it apart into these two pieces because these two pieces are easier to integrate separately. So let's see why. Well, 4, obviously, easy to integrate, right? Just 4x. This 36 being a constant, this is like the B part of this example. We have a constant, A part of this example, where we have a constant up here and then that arctangent business. So we end up with 4x coming from that 4 integral, 36 my constant multiple, and then this, just like back in part A of this example, is just an arctangent. So it's 1 over A arctangent u over A plus c. And then I did go ahead and simplify that 36 divided by 3 to be 12. So this was a really good one to show you how little changes in the integrand can make for big changes in the technique that you use. Okay, so that wraps up section 8.1.